Audio Jungle. Audio Jungle.
Fine. So we'll talk about the SHEAR center now. Okay. SHEAR center. So SHEAR center is basically, it's a point. Okay. It's a point for the any member, structural member. It doesn't mean it is symmetric, unsymmetric, it is closed section or open section, but for all type of the structural member, there will be one point. Okay, and this will be the point through which, if we'll apply the that uh, resultant shear force, okay, then the member will be subjected to only bending a moment. There will not be any twisting moment. So in this way you can define, okay, this will be the shear center. I mean, you are applying the load, okay, if you are applying the shear force, and different point you select, okay, for the shear force you apply shear force over the that member, okay, and somewhere there will be one point, okay, at that point if you apply the shear force, then you will get only bending moment. You will not get any twisting moment. So you will say, okay, this point will be the shear center. Hope you understood. So simple definition, if I say, so the shear center is the point through which, if the resultant shear force acts, then member is subjected to simple bending without testing, without twisting moment. Okay, it will be subjected to only bending moment. There will not be any twisting moment. So this is 1 marks question also. They will ask, shear center is the point where bending moment and twisting moment both will be acting. Only bending moment will be acting, only twisting moment will be acting, none of the above. So shear center is the point where only bending moment will not get any twisting moment. Or another way the definition is, shear center is the point where twisting moment will be zero, called shear center. Okay, that is the very important point for any structural member. So why we are actually, why it is important for the structural member? So as I have already discussed, CG or centroidal of the any structural member, CG. So 2 points once you go for any design for any structural member, so 2 points are very important. One point is the CG of that member. Second point is the shear center also. Why shear center is important? Because you will be aware, okay, this is the shear center. So if we'll apply any force at this point, then only bending moment will not get any twisting moment. So there is no chance of the torsional moment at that point. Only bending will be there. There will not be any torsional moment. So no twisting. There is no rotation, you can say, because of that force where you are applying. If it is shear center, so if you are applying the force there, then you will not get any twisting or you will not get any rotation. You will not get any torsional moment. Hope it is clear to you. Right? We'll write this 2 lines definition. So now the shear center, I can write the definition in one points. It will be better because 3 point of view question they are asking. So we can say the shear center is the point through which, if the resultant shear force acts, then member is subjected to simple bending without twisting. This shear center also called point 2. Also called center of flexure. In few books you may get this also. Center of flexure. It's just for understanding, you can say the shear center is the centroid of shear flow. Okay, centroid of shear flow, where the shear force will be acting, or centroid of shear force, that is enough. So these are the different points I have mentioned. Okay, 3 points you need to remember. All right, moving ahead, we can have special notes. Special notes we will have for the shear center, and these notes are point number 1. Shear center, generally it will not coincide with the centroid of the structural member, okay, but in some special cases it will coincide. So what are the special cases that we should know, because question they are asking for this. So special points for, I must write special points for shear center, okay, and that you need to remember all time. So shear center is always lies on the axis of symmetry, on the axis of symmetry. This point is very important. If exist, because if suppose structural member is what, not symmetric, then the condition will be different, we'll see that. But if it is symmetric structural member, so it is 100% sure shear center will lie on that axis of symmetry. Number 1, this is very important. Number 2, these points are very important, exam point of view I'm saying. Shear center generally does not coincide. Shear center generally does not coincide with the centroid of structural member, except in special cases when the area is symmetrical about both axes. When area is symmetrical about both axes. So what is the mean of it? So shear center, generally it will not coincide with the centroid of the structural member, but there is one specific case when the shear center and that centroid of the structural member will coincide to each other. What is that? If the structural member is what symmetric about both axes. Okay, so we can write the points. It's very important. It's a the corollary of this point 2. I can write 3 as point as a 3. This is very special. So if there are two or more than two axes of symmetry exist. Why I mentioned 2 or more than 2? Generally it is 2 axes like x and y axis, but if more than 2 axes, that means x, y, z. If there are 2 or more than 2 axes of symmetry exist, then shear center will coincide with the point of intersection. This is very important actually. Point of intersection of axis symmetry. I will show the diagram so it will be more clear. Because
in previous slide.
Okay.
Done, sir.
Okay. So for all, I will draw the diagram also. So in this case, same point I'm just going to extend. In this case, shear center of area will be same as centroid of area. Okay, so few structural member need to draw here so it will be clear to you. If it is symmetric about both axes, then what are that member? You can say it's a I section, symmetric I section will be symmetric. If it is symmetric about both axes means what? See, if you talk about this structural member, so I must say this is symmetric about both. So symmetric about both means what? X and Y axis. Please draw proper diagram. I'm not able to do that. So one more try. All right. So it is symmetric about both axes means what? If you check this section, so this is Y axis and somewhere here this is X axis. So if the flange and web both, if dimension is what same, both upper flange and lower flange, this is flange and this is the one flange, So upper and lower flange if dimension is what same. So it will be symmetric about both. So if it is symmetric about both axes, I mean x and y axis, so doubly symmetric, this is called doubly symmetric. It is called doubly symmetric. If any structure member is what symmetric about both axes, so it will be the doubly symmetric. So that time wherever the intersection point of x and y axis will be the centroid of the structural member as well as shear center also. Okay, so in this case shear center of area will be same as centroid. So here this is the CG centroid and this is also the shear center S C shear center. Another structural member, many are there. We just say rectangle, you say circle. Okay, so for this type of any structural member which is symmetric about both axes, if you draw, this is what x axis, this is what y axis. Similarly here also x axis and y axis. So if it is symmetric about both axes, then the centroid and shear center will coincide to each other. It will coincide to each other. CG shear center, CG shear center. Okay, this is what doubly symmetric. This type of member called doubly symmetric. But if it is suppose not doubly symmetric, if it is suppose symmetric about one axis only, then what will be the location of the shear center? So for that also points I have given. What is the point I have given? The shear center is always lies on the axis of symmetry if exists. So at least if it is symmetric about any axis, if it is x axis or y axis, so based on that we have to choose. It is symmetric about x axis, so shear center will lie on x axis. Okay, now we'll see. So another structural member I can draw here. We just draw T section better first. So for this T section, if you check, so if flange here, if this is the flange and it is the same dimension both side, okay, after seeing the diagram only you can say it is symmetric. If this side length b/2 and this side length is b/2, means same, total is what b, and it is equally divided. So you will say it is symmetric about what? It is symmetric about y axis. So it is very clear, if it is symmetric about y axis, then it will be very clear the shear center will be existing on this axis only. But where it will exist, that is the point. Where it will be existing. So if you check, if it is symmetric, okay, if it is symmetric, so where it is going to overlap. So this is A, this is B, C and D. If you check, if you overlap this, so overlapping you may get here, I mean this portion D will be overlapped to A, C will be overlapped to B. About this axis, here will be your shear center. This will be your shear center. Where will be the CG? So obviously CG will not be this. CG will be somewhat below, because for T section we had calculated CG also. So now this will be the CG and this will be the shear center. Similarly, any other section also you can take. You can take L section if you want. So obviously if you check this L section, so you just see even it is not symmetric about x-axis, it is not symmetric about y-axis. But if you draw one axis here like this, if you draw like this, okay, so if you overlap this part, okay, so it will be like this. Check this section. I'm taking this portion. So how it will come? I mean, if you take this part only up to here, this part, so it will be like this. I say this is P and this is Q. If you draw, so P and Q will like this. Now you draw one axis here. So say this is nothing but R axis, you can say. Say about R are this P and Q. If you overlap this, then P will overlap to Q. So about R are this portion will be symmetric. So where is the chances of the shear center for this L section? So you can say it will be here. Check the points. Somewhere here. So shear center will be existing at this point. Hope you understood by this diagram. Where will be the CG? So CG definitely, you have solved the L section. So CG you may get here somewhere. So this is the CG and this is what shear center. If I say for this section, the same L section, but it is.
Sir, how CG will be there? I mean, L section is here.
Because see, very simple. This portion is what? I mean, mass distribution here and mass distribution here. It is not symmetric. Yes or no? So it is sure the CG will not lie on this below section. In fact, CG will not lie over this upper section. In between somewhere CG will be lying. It is like for any structural member, it is not necessary CG will lie always inside the structural member. CG can lie out of the structural member also. Yes or no? In fact, shear center also, it is not necessary it should lie inside the structural member. It can lie outside also. I will show you for the channel. So even though if you calculate also x bar and y bar, so you will get here. Okay, because it is not symmetric even about x-axis and not symmetric about y-axis. So if any structural member which is not symmetric about x-axis, even not symmetric about y-axis also, so for that CG will not lie on x-axis, not only on y-axis. It will be in between. That is the definition. Okay. In fact, if you calculate CG, so you may get the result. I mean, if you see that time when I had taught moment of inertia and CG calculation, so I said take any textbook for the practice for moment of inertia and CG. So if you solve for L section, you may get CG here. And for this type of section, if you check, so here also CG you may get somewhere here. This will be the CG location out of the structure. And where will be the shear center? So shear center will be like here, somewhere here. This will be the shear center. Is that clear?
Yes, sir, clear.
Right. Now coming to the next kind of structure. Now you can draw a structure like this. So all type of structure I am giving because sometimes it may hit somewhere. Suppose this is the another structure. For this structural member, if you check, so definitely CG will not be here or CG will not be here. It will be in between somewhere. So I must draw. I can say this is the one axis, which is Y. But shear center will lie on symmetric axis of symmetry. So I can say this is the Y axis. So in this situation, shear center will lie here. This will be the shear center. and somewhere here will be the CG if you calculate this type of structural member, because it's a channel, kind of channel you can say. So, and obviously that even though if you check the mass distribution for both sides, so at the resultant you will get the CG. So if you check for this structural member, so resultant will be in between. So CG is what, it's a centroidal, like where the total mass is what existing. That's the point. So for this type of section, CG will lie here and shear center will lie here. So I mean, here I'm just saying directly, but if you want, you can calculate also. So you will get that. Okay. Because for all type of the structural member we cannot go and we cannot calculate for, so for that reason you should at least aware with that. Okay, CG will lie here. Fine. So the point is, if you go for the shear center and even it is not symmetric about x-axis or y-axis, so wherever you will get the joint, so at the joint, or you can say at the junction point where the two section or any two rectangular member meeting to each other, so for that junction point will be the shear center. That also you can remember. So if you say, I will add one more point here, it is third point. So now we'll write fourth point. We can mention here, we can say if a section is made of two narrow rectangles, then shear center lies on the junction of both rectangles. Example, we can take any one. I can say this is the one rectangular member, okay, and suppose it is connected with this like this. So wherever the meeting point of this, okay, so that will be the, see, they are meeting to each other at this point. So this will be the shear center. This will be the shear center. Any example you can take where the two structural member they are meeting each other will be the shear center, or you can take this one also, it's your choice. Any example you can take. Okay, so even though you can say this is the doubly symmetric also, you can say this is the doubly symmetric also, so this meeting point for this will be the shear center, and here this will be the, because it's a doubly symmetric also, CG will also lie here. Shear center and CG both will lie because it's a doubly symmetric. So next we have a calculation of shear center. This is very important. Sometimes 2 marks in GATE aerospace it was asked. Okay, so it's very simple only. So like for the even simple section will take like C section or I section, and I will show you how it comes. Rest you need to remember the formula also, because every time we not required to go for the derivation and all. So all right, so basically in examination they had asked for the C section, so it's an open channel, basically thin walled open section. In examination what they had asked, it was thin walled open section, and basically it was C channel. Okay, so for the C section or channel, we can say the shear center direct formula I will give. Actually it's a derivation, but I will suggest derivation not required here. Okay, so I can say here this is the C section, and for this we need to calculate the shear center. All right, so symmetric only. If I say axis I am taking, suppose here this is the x-axis we have. If I say load is what applying for this section, okay, now if you calculate the load for the you just apply somewhere, suppose the shear center location is what at E. E is the distance, and at E distance, and this E distance is what, from where, from the this wave. This is what wave, and just say this is what flange. Okay, and I'm saying the load is what acting here, SY, because axis is what x-axis here, and this is what y-axis here. Okay, so definitely E is the distance of the shear center, so just say this point will be the shear center point. So now if you are applying this, and what is the SY? SY is the shear load. If you remember, we had already shear force, that formula we had derived, or we had seen shear force distribution, and that formula, if you check, it was tau, that was the shear stress, different notation always, and the load was SY, and this was AY bar divided by, if you remember, it was IT. So in previous what I had taught there, it was that formula, if you recall, so it was Q is equal to shear force F into AY bar divided by IB. This was the formula I had given in my shear force distribution lectures, like after bending I had taught. So the same formula we have, instead of Q, now shear stress I'm writing by tau, instead of F I'm writing S. Why? Because it is acting in y axis or in y direction. A is the area, it was small a. Y bar is the location of CG. I is the moment of inertia, and there it was breadth. Okay. Now here it is thickness T, because you are talking about the thin section. So this will be the formula. Okay, so because of this shear stress, we can have a shear stress distribution. So any if you take C channel, and for the C channel, if you draw the shear stress distributions, you may get like this, that you should aware with this. Okay, so for the C channel, if you draw the shear stress distribution, so the shear stress distribution will be like this, and shear flow also you may get here. Okay, suppose this is the C channel. So for this C channel, if you check the shear stress distribution and shear flow, so shear flow, if you load is what acting, shear stress will be acting, so shear flow you may get because of the shear force, shear flow you may get like this. This will be the shear flow. Okay, this is called shear flow. This is the shear flow. If you check the shear stress distribution, so I hope you remembered, because it is the, you know, in coursework, BTech coursework, this problem might you have solved. So the shear stress distribution will be like this. If you calculate, so this value will be, this is the shear stress distribution. Okay, and this is for the flange, and if you go for the wave, so it will be a parabolic. So this parabolic distribution will be like this here. So this is the shear stress distribution, right? Just like for the I section, T section you might have seen. So similarly we have a shear stress distribution for the C section. So this is the shear stress distribution. Okay. So basically where more shear stress you will get, in wave you will get. This is called wave. This is also, we need to remember, this is called flange. So for single marks they can ask where maximum shear stress will get in case of C channel. So you have to say in wave. So this is the tau max. Maximum shear stress you will get in the wave portion. Okay. So for this I can say we can have this width is nothing but B for this section, I mean for the flange. Obviously similarly here also, because it's a symmetric, so it's a symmetric about x-axis, so I should draw x-axis here first. So this is the x-axis. Just say from this to this length is h by 2. Similarly here also you can say this is h by 2. Okay, I must say, because most of time, because if it is a thin, so obviously this thickness will be same for both. So this is the, you know, this is what wave, so thickness of wave is nothing but W, and this is what flange, thickness of flange is nothing but TF. I should write thickness of wave thickness of flange. Okay, that you need to remember. All right, if you go for the as I say, it is symmetric, so whatever the value here of shear stress, it is tau 1. Similarly here also it is tau 1, but this will be the different portion, it will be tau 2. That is the shear stress distribution, always remember. And this is what shear flow. Why you are getting this shear flow and all? Because of the shear load, you have applied that. Okay, so if you say what is the shear center, so shear center is nothing but centroid of the shear flow, centroid of the shear flow. So for that reason, if you check the centroid point of the shear center, so because this is the shear flow, if you combine all three and centroid of the shear flow, if you check, so where the more shear distribution you are getting shear distribution more and more near to the wave, right, near to the wave. And which side you are getting just opposite side, where if this is the C channel, so opposite side more shear distribution you are getting. So for that reason you will get shear center here. That I told you, shear center definition also, it is the centroid of the shear flow. So and obviously shear distribution you may had here also, so more shear stress distribution. So shear center you can say will lie this side. If C section is what like this, if C section is what like this, so where shear center you may get shear center here. This will be the shear center. If this is the C channel like this, so where shear center you may get here, this will be the shear center. If this is the C channel, so where shear center you may get, this will be the shear center. In that way you can understand, okay? Many explanation we have, but ultimately the goal is to remember the formula, okay? Because derivation at all not important for the competitive one-day exam. So for the same diagram what I have shown you here, for the same diagram I'm just going to write the location of shear center. So location of shear center for this diagram I'm going to write. Why it is important? Because dimension you need to remember, otherwise it may have it may give the problem, okay? So dimension you need to remember. So particular for this we are writing shear center for this section. So because it's a thin, so for the thin you can say this is the medial line. From the medial line the total distance is h/2 from the x-axis, and below side it is h/2, total will be h. So because this is the thin section, thin channel, so I am just drawing only one line. For thin we can consider this is the one line, and now this is what axis, okay, this is what x-axis. So your shear center you somewhere here you can say it will lie, and this will be the location of the shear center here. Because this is the h/2 and this is h/2, or you can say the whole, because it's a thin, so this value you can say h. All right, now for this particular, what will be the location of the shear center? So I can write here location of shear center. This is nothing but B, okay? So the formula for this is nothing but E is equal to B square H square, thickness of the flange, both side it is same, no? Thickness of flange. So TF divided by 4IXX, because this axis is XX. So this is the formula. Only this formula, if you remember, it will be very helpful for you. Otherwise, if you want derivations or derivation separately, I will provide. Here I must say, because for one day exam it is not important, so all the dimension, distribution, everything I have explained, but this formula directly I am giving to you. This formula will come after the derivation. Few steps we have to do. So our date will take 30 minutes if you derive, but it's a simple only, okay? We'll solve one problem based on this. Similarly, we can write for the I section also. But for the I section, as you know that shear center, if it is symmetric I section, okay? So shear center will be location of CG. If you know CG, then you can say this is the shear center also. Like in previous already I have discussed here. See, here I have shown you if it is the doubly symmetric I section, so CG and shear center must be same. So for doubly symmetric I section, not required the separate formula for the shear center. You know the location of CG formula, use that and you get the shear center. Now I will give the formula for the unsymmetric I section. Okay, probably it will help you, okay, to get the result. So this is the case one, okay, this is the case one. This is very important here. In GATE they had asked, okay, directly formula, I mean C channel they had given to you. Case 1. Now we'll go for the case 2. What is the case 2? So for unsymmetrical I section I'm going, okay, unsymmetrical I section. I'm not going for the C section, okay. I'm not going for the symmetric I section because it's a CG location. I'm repeating many times because you need to remember that, because sometimes directly they had asked, so you should know that result. Now, so unsymmetric I section means what? I will take this. Okay. So obviously this will be the flange. In middle, this is the wave. So you can say this flange, if this is what y-axis here, and this is the x-axis. Okay. So you can say that it is symmetric about x-axis. That is true, no doubt about it. But it will not be symmetric about y-axis. Why? Because dimension I'm giving different. What is the dimension for this flange? I can say this side dimension is nothing but I say b2, and this side it is nothing but b1. So this dimension is not same, hence it is not symmetric about y-axis. But what about x-axis? It will be symmetric. You can check it. It will be symmetric about x-axis. So it is 100% sure your shear center will lies on the x-axis. That is true. But we don't know which side. I mean, we don't know what will be the location. So for that, we should have a formula. So I can say, because it will be treated as a C channel, both two C channel we have, okay, two C channel we have. This is the one C channel and this is the another C channel. If you check, this is the bigger one, okay. So mass distribution more here. You just say it is 200 mm, this is 100 mm. So this is the bigger channel, and this is the smaller channel. So for bigger channel, if you check the resultant, so shear center, I mean hypothetically you can think, so shear center may lie this side, but it will be over the, I mean it will lie on the x-axis. So this is the x-axis, and from x-axis at e distance your shear center will be here. So just say this is the shear center at e distance. Now what will be the formula for this? Okay, that is the important. You just say again, if you can convert this in, thin section, because if you talk about the thin section, so only single line you need to draw, thin unsymmetrical I section. That is the thin approximation. I had taught you what is a thin approximation. So thin symmetrical I section, unsymmetrical I section. So what is the approximation? With the help of this approximation, we can redraw this. So if you redraw this, then thin approximation will be like this. See, this is the thin approximation. This is the I section. Okay, you just say this is what x-axis. Somewhere here, this is what shear center, and this distance is, this is shear center, and this distance is nothing but E location. I say this length is nothing but B1, and this length is nothing but B2. Remember it. And this thickness is nothing but, it's a flange, so TF, and obviously both sides it is TF. Thickness will be same here also, TF. It's not changing, TF. And the distance is nothing but, this is what? H by 2, and this is H by 2. The whole distance I must say, because this is nothing but H. Now for this unsymmetrical I section, if I will write position of shear center, this is very, very important here. Position of shear center. Then what is the value of E? So E is equal to h square thickness of flange b1 square minus b2 square 4ix. This is the formula of the shear center. This is very, very important, very, very important. For symmetrical I section, not required because it will be the CG location. But for the unsymmetrical I section, CG and shear center will not be same. Okay, shear center and CG will not be same in case of unsymmetrical I section. So in this situation, you should, remember the formula of shear center here. This is the shear center. There should not be any confusion. Okay, there should not be any confusion.